In example 8, we're still optimizing a multivariable function. But like with example 7, we're going to see something a little bit different happen in part B. We want to look at how we solve or how we proceed with a scenario like that. We'll start off by finding the first partial derivatives. N sub x will be 3x squared minus 6x. And n sub y will be 8y. This means we'll take 3x squared minus 6x set equal to 0 and 8y set equal to 0. Solving the second equation is very simple. That's just going to be y equals 0. But to solve the first equation, we'll first need to look at factoring. We can factor out a 3x that's common between these two terms, leaving us with x minus 2 is equal to 0. Now we solve two different equations. We solve 3x equal to 0, which will give us 0, and we solve x minus 2 equal to 0, which will give us positive 2 as a solution. We have two x values and a single y value, but to find a critical point, we have to have an xy pair. What that means is each of these x values is paired with that same y value, meaning we have two critical points in this scenario, 0, 0, and 2, 0. That also means we have to test both points to see which one is a maximum, minimum, saddle point, or if the test is inconclusive. We'll find our second derivatives. N sub xx will be 6x minus 6. N sub xy is equal to 0. N sub yy is equal to 8. And n sub yx will be equal to 0. Now we also have a different case in part C than what we've seen before. One of our second derivatives is still a function of x, meaning to evaluate or to plug that into our expression, our formula for d, we'll have to evaluate 6x minus 6 at the given value for x. So we'll first find d of 0, 0, meaning we'll take 6 times 0 minus 6 times 8 minus 0 times 0. This will end up giving us negative 48, which is less than 0. I'm running out of room to write on my screen, but that's less than 0. Then we'll find d of 2 comma 0, which will be 6 times 2 minus 6 times 8 minus 0 times 0, which is just 0, and we'll end up getting positive 48, which is greater than 0. For 0, 0, we ended up getting a value for d that's less than 0, which tells us that 0, 0 is a saddle point, meaning it's neither a maximum nor a minimum. For 2 comma 0, we ended up with a positive value for d. Then the next thing we need to check is n sub xx, evaluated at 2 comma 0, which means we need to figure out what 6 times 2 minus 6 is, which will be 6, which is greater than 0. Since d is greater than 0 and the second derivative n sub xx evaluated at that point is also positive, greater than 0, that means we have a local minimum at 2, 0. So in the event where we come up with more than one critical point, we need to calculate a value for d for each pair, and we'll come up with two results based off those. One of those still could be that inconclusive result, but we need to look at classifying each point separately.